All right, so this next result is actually something that we've alluded to a little bit already. So back when we were first chatting about this general notion of divisibility, we had a few examples of some things that were not divisible. For example, if I hand you this number 45,631 and ask you to divide this thing by 11, what's going to happen is that you're going to see this quotient of about 4,148 emerge, but we know that this 11 is not going to divide nicely into this thing because of this existence of some non-zero remainder. So in this situation, I'm going to have that 45,631 is not divisible by 11 because there is a remainder of 3. If I want to phrase this in this new divides terminology, that is to say that 11 does not divide 45,631. So this actually does introduce a slightly new piece of notation. We have this general notion of divides as this vertical line. Well, if I want to introduce something that says does not divide, all I got to do is just put a slash in front of it. And that's pretty common. Anytime you're working in something in math, if I just want to say not, you can just put a big old slash in front of it to say that 11 does not divide this thing. And the reason for this, again, is because there is a non-zero remainder. But in this case, all hope is not lost. There is still a lot of good information that actually ends up occurring in this situation. I have a really nice interplay between this kind of big number, this big 45,000 blah 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 number, and its connection between that and its divisor 11. The question is how many times does 11 actually go into 45,631? Well, the answer to that question is going to be that quotient. I know that it's going to go into that thing 4,148 times. I just know that it's not going to be perfect. So the idea is that I'm going to try to put in as many 11s as I can into that thing until I get down to a stage that I have a couple left. In this case, I only have 3 things left over. Everything else is going to be this nice grouping of 11. So if you wanted to, you could write 45,631 as a whole bunch of little 11s. In this case, 11 added together 4,148 times, and you'd have a little pile of 3 things left over. So what the division algorithm actually says is that you can do this anytime you want to. Anytime you give me 2 numbers, in this case, hand me some really big number, I'm going to call this thing A, and hand me another little number, in this case this divisor D, I can always find this quotient and this remainder. In this case, I can find a Q and an R that gives me this really nice representation that we have down below. It's the idea that I start with this big thing. I'm going to ask how many times does the little thing go in there. So that's going to give me this answer of Q. And then I'm going to have this little leftover piece. So that's all the division algorithm says, is this kind of classic grade school kind of computation or arithmetic that you've seen over and over and over before. It just lays it out in this kind of one nice horizontal row. There's a little bit more underlying a lot of this. It's going to be this big fact that says unique, and we're going to come back to that later, this idea of why does the Q and the R, why do they actually have to be unique, as well as a little bit of information on where should that R live. In this case, I want to find the smallest possible remainder that I can. So for right now, we're just going to state this thing as is, just so I can introduce some notation and kind of see where all of this comes into play when we're chatting about divisibility and slowly entering this world of congruence. So like I said, we'll see a lot more about this division algorithm later, as well as kind of a sketch proof of this thing. For now, it's just kind of a lead into some of the notation. So the notation that goes with this, as well as the kind of terminology, is going to be that initial number that you give me, that kind of big number, is often referred to as this dividend, which is hopefully consistent with what you've seen kind of from a college algebra course and things like that. Whenever you start talking about dividing polynomials and things like that, you start off with your initial big polynomial. What you're going to do is you're going to try to divide it by some divisor. So in this case, the divisor is going to be referenced as this little d. And then the 2 things that are kicked out of it are going to be the quotient and the remainder. In this case, that little q and that little r. That r is going to be the thing that we're going to be most interested in about. You can kind of see already is that r is going to indicate whether or not something divides nicely. If the r is 0, I know that I have this perfect notion of divisibility. And if I have some non-zero remainder, something else entirely is going to occur. And as I kind of alluded to earlier, we're going to start to put things into various camps. The idea is that if I have the same type of remainder, that's actually going to shed some light on kind of what's occurring in this case. Kind of as a really quick foreshadowing, the idea is that if you try to look at dividing by 2, that's actually going to give you information about whether or not a number is going to be even or odd. If you have a 0 remainder when you divide by 2, you're going to be even. And if you have a remainder of 1 when you divide by 2, that's going to tell you if you're going to be odd. So in that case, we can start to generalize this notion when we start dividing by things that are not just 2. We can start dividing by much larger things to really give us information on about what's going on. Okay, so let's see if we can actually apply this division algorithm on a couple different pairs of numbers. So in this case, we're going to first look at trying to find the quotient and remainder when I'm given a dividend, in this case of 100, and a divisor of 15. And I'm actually going to try to sketch out two different results for this thing, one of which is going to be the old school kind of elementary school kind of long division approach, and the second one's actually going to be the way that you could code this thing if you ever wanted to actually just have a little calculator that kicks out all of these things. We get this nice kind of single line algebraic expression that tells you exactly what the quotient and the remainder should be. Okay, so first up, so in this case I'm going to call this solution 1, not an exclamation point. Well, what else? I'll put an exclamation point afterwards saying, yay, it's solution 1. Okay, so I'm going to try to see how many times does 15 go into 100. So in this case, 15 into 100. What's going to happen is that that goes into 106 times, because 6 times 15 is actually 90, and you see that I'm going to have a remainder of 10. So in this case, this thing right here is going to be my quotient. That thing is going to be my remainder. And I do in fact see that 100 then has this really nice representation. It's going to be viewed as 15 times 6 plus 10. So in this case, my A is equal to D times Q plus R. All right, so that's pretty nice. It's not so bad. The second solution is actually the slightly slicker one to start seeing, and it looks a little bit gross the first time you see it, but it does become pretty nice actually once you kind of get the hang of what's going on. The idea is what I'm actually doing in this case when I'm taking 100 divided by 15. I'm just taking the whole number component of that thing. I don't care about if there's any possible decimal or anything that occurs afterwards. So what's going to happen is that if I take 100 and if I divide it by, in this case, 15, if you plug this into your calculator or something like that, it's going to give you 6.666666666 going on and on and on and on forever. So in this case, I'm going to view this as 6.6. In this case, this repeating 6 I'm going to indicate with this over bar. So what I want to see is I want to see that that quotient is just that whole number 6 that emerges. So in this case, the function I'm going to use is referred to as the floor function. For those of you in some computer science classes, you might have actually seen this word or this command at some point in time. In the math world, we typically denote this thing as these vertical bars that have these kind of little underlines on it. So that's going to say the floor. So it's kind of the lazy man's round down in this case. I'm going to take this kind of 6.66666, and I'm going to round this thing down to the nearest integer. So in this case, it's going to kick out a 6. So like I said, it's the lazy man's round down, but it works really nicely. There is the equivalent version of a ceiling, which is going to be the lazy man's round up, and that's going to be indicated with the same type of thing, except for those little bars are on the top. So in this case, you can see that that 6 is actually going to be the quotient that emerges. So anytime you want to find your quotient, all you got to do is just compute kind of the top number divided by the bottom number and just round down to whatever the nearest integer is going to be. So the question is then, how do I take that information of what my quotient is to try to kick out what my remainder is? Well, if you look at this, what's going to happen is that I know that 15 is going to go into 106 times. So all I got to do is I got to see whatever's left over in this situation. So I'm going to take that 100. I'm going to then break off as many of these things that I can. So in this case, I'm going to subtract off the 15 in this case, multiplied by the 6, and you're going to see that at the end of the day, that's going to kick out that 10. And that's exactly what my remainder is going to be defined by in this case, is that it's going to be created by taking that initial number that I have, and then I'm going to break off 15 times however many my quotient is going to be. So in this case, I do in fact see that I have a remainder of 10 and a quotient of 6, and I can go back and double check to see that, hey, actually in fact, 100 is going to be 15 times 6 plus 10. So the idea behind the second solution is going to be that my Q is always going to have a nice representation. It was simply given by this 100 over 15 in this floor notation. And then my R is going to be obtained by taking that initial number 100 and then subtracting off 15 by however many that Q kicked out. So in this case, 100 over 15 and the floor of that thing. So here's where you can start to see a little bit of the coding side of this, is that all you have to do to find the Q and the R is just execute those two lines. And once we're done with the next couple of examples, I'm actually going to go back and show you the official line kind of written out in a much more general setting. But for now, kind of just seeing where all those pieces come into play. What's really nice about this transition from kind of this first solution into the second solution is that it makes it really easy to go from trying to talk about quotients and remainders with positive numbers to actually introducing this. I'm trying to swipe and it's not working. Okay, to starting to introduce this notion when I start to look at negative numbers. So in this case, if I switch from being A being 100 to A being negative 100, so in this case, let's say this is example B, that same approach that we just got done looking at is going to carry through. I can find my Q really easily. What's going to happen is that my Q is going to be this floor of negative 100 over 15, which in this case you're going to start to see something really kind of interesting occur. I'm going to have this negative 6.6 repeating, and the floor of this thing is going to kick out a negative 7. So for those of you in some of the computer science world, this may look a little bit different. This is where I do in fact want to use the floor function and not just the kind of nearest integer function. So I don't want to just use integer version because I'm actually going to want to round this thing down to negative 7. So next up is going to be the idea of what should my remainder then be. Well, my remainder is going to be my initial number that I started with, so negative 100, minus my d value in this case, which is 15, multiplied by this q value, which in this case was my negative 7. And if I go and actually compute all of this stuff, it's going to be what? Negative 100, and then this is going to actually kick out something like a positive 105, which at the end of the day kicks out a remainder of 5. So you see a subtle difference happens when I'm actually looking at a being negative 100. I'm going to have a quotient of negative 7, which already looks kind of funky, and I'm going to have a remainder still in this case of 5. So what's happening is that I can see that I have this factorization, my a equals dq plus r. For negative 100 is going to look like 15 times negative 7, in this case plus 5. So it's a little bit different than that last example, and you can see that that negative sign is going to have a really important thing actually occur. I actually do get different remainders. This first one had a remainder of 10, whereas this situation actually has a remainder of 5. So as I kind of alluded to a few times already, we actually do have a slightly more formal version for what those q's and r's happen to be given by. In this case, you can see the kind of formal structure actually takes shape. The idea is that if you give me my kind of a, this dividend, the big value that I'm starting with, and I try to divide it by some d, my divisor in this case, well, my quotient is simply going to be the quotient of those two things and then take the floor of that. So take a divided by d and then round down. Where then my remainder in this case, that little value of r, is going to be obtained by taking your initial number and then subtracting off your kind of divisor multiplied by that new quotient. So in this case, you could alternatively write this as a minus dq in this case. So it's pretty nice you get these kind of slick computations to actually find your quotient and your remainder. We actually introduce a slightly new piece of notation, which for those of you in the computer science world, you may have actually seen a little bit of this. The first of which is going to be my q, which is viewed as my divisor in this case. So there is this a divided by d, this div notation. And we also have the slightly more important one, this term of mod. So in this case, I'm going to have a divided by d is going to introduce a remainder. And in this case, it's going to be this modulus. And so in this case, I can also reference this as a mod d. And a lot more about that as we go into some of this congruence world, that this kind of modulo world is going to become a really, really important thing. So for now, it's just kind of a weird little notation that we're going to really push hard in a little bit.